Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1874 address by George Johnstone Stoney, delivered to the British Association for the Advancement of Science in Belfast, represents a monumental exercise in theoretical synthesis, a moment where disparate threads of 19th-century science were woven into a singular, audacious proposition. The paper, titled On the Physical Basis of Long-Distance Electrical Action, sought to provide a mechanical and material foundation for the phenomena of electricity, moving beyond abstract laws to a tangible, quantifiable reality. This essay will undertake a profound and systematic evaluation of the internal claims presented within Stoney's work. It will proceed section by section, examining the logic, evidence, and conceptual frameworks he employed to argue for his most enduring contribution the existence of a definite, elementary quantity of electricity, a natural unit he would later christen the electron. We will explore the architecture of his reasoning, from its basis in ether physics to its culmination in a calculated value for this fundamental charge, assessing the intellectual rigor and speculative leaps that characterize this foundational document in the history of physics. Section 1. The ethereal medium. As a necessary precondition, Stoney initiates his argument by positing the necessity of a physical medium, the luminiferous ether, as the sole mechanism for transmitting physical action across space. He establishes this premise as the bedrock upon which his entire theory of electrical action rests. His analysis opens with a firm alignment with the principles of Faraday and Maxwell, who conceptualized space as being filled with a substance capable of sustaining fields and propagating waves. Stoney's claim here is that any theory of long-distance force, including gravity and electricity, requires a contiguous intervening medium to be physically coherent. He argues that the concept of unmediated action at a distance is a mathematical convenience that obscures a deeper physical truth. The evaluation of this initial claim reveals its strategic importance. By committing his framework entirely to an ether, Stoney provides a physical stage for the events he is about to describe. This move, while common in his era, has profound implications for his subsequent arguments. All electrical phenomena, in his view, must be interpretable as states of strain, motion, or other modifications of this ether. The strength of his claim here is its consistency with the dominant paradigm of his time. Its vulnerability, from a modern perspective, is its complete dependence on a theoretical construct that would later be discarded. Within the context of 1874, however, his argument is logically sound, providing a necessary physical ontology for the electrical charges he will soon introduce. These charges are conceived from the outset as localized phenomena, interacting with and through a universal plenum. Section 2. The argument from electrolysis and the definite unit of charge. The intellectual core of Stoney's paper resides in his synthesis of Faraday's laws of electrolysis with the principles of the kinetic theory of gases. It is here that he constructs the central claim of the work, the existence of a specific and universal quantity of electricity associated with each chemical bond. He meticulously reasons from Faraday's first law of electrolysis, which states that the amount of a substance decomposed is directly proportional to the quantity of electricity that passes through the electrolyte. Stoney elevates this empirical law into a microscopic principle. He combines it with the understanding of chemical valency, recognizing that the liberation of a monad atom, like hydrogen, always involves a certain quantity of electricity, while the liberation of a dyad atom, like oxygen, involves double that quantity. The crucial intellectual leap occurs when he connects this chemical observation to the atomic hypothesis and Avogadro's principle. He argues that if matter is composed of a definite number of atoms in any given volume, and if chemical decomposition involves a definite quantity of electricity per atom, then there must exist a single, fundamental unit of charge. He explicitly states that for every chemical bond that is ruptured in an electrolyte, a certain quantity of electricity traverses the electrolyte, and that this quantity is absolute and universal. The evaluation of this section's claim must acknowledge its sheer brilliance and logical force. Stoney is essentially performing a dimensional analysis on nature itself. He identifies two well-established quantitative laws from different domains, chemistry and electricity, and shows that their intersection implies a new fundamental constant of nature. His evidence is the consistency of electrochemical equivalence. His methodology is one of rigorous analogical and deductive reasoning. He transforms the macroscopic, continuous flow of current in a wiring to a microscopic, discrete procession of charge units, each tethered to an atom. This argument is powerful because it is independent of any specific mechanical model of the atom or electricity. It is a conclusion derived from quantitative relationships. Section 3. The first quantitative estimation of the elementary charge following the logical deduction of a fundamental charge unit. Stoney proceeds to the ambitious task of calculating its value. This section of his address represents a pioneering effort in quantitative microphysics. To perform this calculation, he required two key pieces of information. First, the total charge required to liberate a known number of atoms in electrolysis, and second, an estimate for the actual number of atoms in that sample. The first value was readily available from electrochemical experiments. For the second, he drew upon estimates derived from the kinetic theory of gases, a field to which he himself had contributed. He utilized a value for the number of molecules in 1 cubic millimeter of a gas at standard temperature and pressure, which he cites as being on the order of 10 to the power of 18. Combining this number with the known quantity of electricity required to decompose the corresponding mass of water, he performed a direct division. The calculation yielded a value for his fundamental unit of electricity, which he expressed in the scientific units of his day. In modern terms, his estimate was approximately 1 times 10 to the power of minus 20 coulombs. An evaluation of this claim must separate the logic of the method from the precision of the result. The input data, particularly the estimate for Avogadro's number, were inexact by modern standards. Consequently, his calculated value for the elementary charge was about an order of magnitude smaller than the currently accepted value. However, the profound significance of this section lies in the methodology itself. Stoney demonstrated that it was possible to reach across scales from macroscopic laboratory measurements of charge and mass to deduce a property of a single, unobservable entity. The intellectual architecture of the calculation is sound and prefigures the very kind of reasoning that would become central to particle physics. He established a tangible numerical target for a theoretical concept, transforming it from a philosophical abstraction into a physical quantity awaiting more precise measurement. The slight irony, of course, is that a more accurate value would await a direct measurement by Millikan decades later, yet the conceptual pathway was laid out here with stunning clarity. Section 4. A conjectural model of molecular motion and ethereal strain. Having established the existence and approximate magnitude of the elementary charge, Stoney ventures into a more speculative domain, attempting to describe its physical nature within his ethereal framework. He proposes a detailed mechanical model for how this charge unit, which he conceptualized as being attached to an atom or molecule, interacts with the surrounding ether. He imagines a molecule in a gas as a system in motion, executing complex trajectories. The atom, with its associated definite charge, is described as having its own orbital motion within the larger molecular system. This motion, he argues, imparts a corresponding periodic disturbance or strain into the surrounding ether. Electricity is thus pictured not as a substance in itself, but as a state of the ether, specifically a form of wave motion or vortex, that is inextricably linked to the moving atom. He speaks of wavelets being propagated from each molecule. The evaluation of this section's claims reveals the characteristic ambition and limitation of Victorian mechanical philosophy. The model is deeply imaginative and demonstrates a powerful drive to unify diverse phenomena under a single, intuitive, mechanical schema, he is attempting to build a visualizable bridge between the discrete world of atoms and the continuous world of the ethereal field. However, these claims are entirely conjectural. Unlike his argument from electrolysis, this section lacks a direct empirical or quantitative foundation. It is an explanatory sketch, a plausible fiction designed to give substance to his more rigorous conclusions. It serves to illustrate how such a system could work, rather than proving that it does. The intellectual wit here lies in observing the Victorian physicist's comfort in constructing such elaborate, clockwork universes of the mind, a testament to an era confident in its ability to mechanically model all of reality. This part of his work, while ultimately superseded, are valuable for understanding the intellectual climate as conceptual tools available to theorists of his Section 5. The connection between atomic charge and optical spectra. In the culminating section of his argument, Stoney forges a profound and prescient link between his model of orbiting atomic charges and the phenomenon of optical emission spectra. He claims that the specific, fixed frequencies of light observed in the spectra of glowing gases are a direct result of the periodic motions of his fundamental charge units. His reasoning is direct if each atom has an associated charge, and if this charge is in a state of regular, periodic orbital motion, then according to the principles of electromagnetism, it must radiate energy into the ether at a frequency identical to its period of motion. He points to the existence of sharp, distinct spectral lines as powerful evidence for the existence of equally distinct and regular periodic motions within atoms. He argues that the complex spectra of molecules could be explained by the superposition of the fundamental frequencies and harmonics produced by the various orbital motions of the constituent atoms and their charges. In evaluating this claim, one must recognize it as a conceptual masterstroke. Stoney is effectively proposing the first rudimentary theory of quantum transitions, decades before the idea of quantized energy levels would be formally developed. He correctly identifies the origin of spectral light in the dynamics of subatomic constituents and intuits that the discreteness of the spectra reflects a corresponding discreteness in the structure or motion of the atom. The claim's strength is its immense explanatory power. It provides a physical mechanism for a well-known but deeply mysterious phenomenon, linking the domains of chemistry, electricity, and optics into a coherent whole. While his mechanical model of classical orbits was incorrect in its details, his fundamental insight that atomic structure dictates optical spectra was entirely correct. This section elevates his paper from a clever calculation into a sweeping theoretical vision, demonstrating how the concept of a fundamental unit of charge could unlock mysteries far beyond the realm of electrolysis. Conclusion. George Johnstone Stoney's 1874 discourse on the physical basis of long-distance electrical action stands as an extraordinary monument to the power of theoretical reasoning in physics. A close evaluation of its internal claims reveals a work of two parts, a structure of rigorous deduction buttressed by imaginative speculation. The central, enduring achievement of the paper is its logical and quantitative demonstration of the existence of a fundamental unit of electric charge. By masterfully synthesizing Faraday's laws with the atomic theory of matter, Stoney constructed an argument for the electrine that was both conceptually sound and numerically grounded, a landmark of 19th century thought. His calculation, though reliant on the imprecise data of his era, established the correct methodology for determining the magnitude of this elementary constant surrounding this solid core. His conjectural models of ethereal mechanics and orbital charge motions, while reflecting the transient philosophical commitments of his time, serve a vital purpose. They provided a plausible physical narrative that connected his abstract entity to observable phenomena like spectral lines, revealing a profound intuition for the relationship between microscopic structure and macroscopic properties. The paper as a whole is an exemplar of scientific creativity, a demonstration that a new fundamental entity, can be logically inferred and quantitatively characterized long before it can be isolated and directly measured. Stoney provided the definition, the name, and the first approximate value for the particle that would come to define the 20th century, securing his place as a quiet and profoundly insightful architect of modern physics.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.